So the redox reaction is related to reversible reaction kinetics, reversible reaction. Reaction kinetics, in this reaction kinetics, we'll discuss the factors which affect the rate or the speed of the reaction, how different factors such as concentration, pressure, temperature, catalyst can alter or affect the speed or the rate of reaction. And the second part is the reversible reaction in which the reactant can form a product, whereas product can decompose and form back the reactant. So first is reaction kinetics, the speed of the reaction. So as we know, when a reaction occur, how a reaction or chemical reaction occur or a proceed, we have the particle example. These are the particles of the reactant. The red spots are representing the reactant particle as well as the black spots. These are the reactant particle, like we have A and B are reacting with each other. A is example red in color and B is black in color. So A and B are reacting with each other, and as a result, when they combine, they produce C. So how a product C is formed, how A and B are converted into C. Basically, the particles, they are moving. As the particles are moving, they collide with each other. As a result of the collision, as these particles are hitting each other, they are colliding with each other. So as a result of the collision between the particles, they will form a product. So this leads to a formation of a product. But not all the collisions are effective collision, because maybe like A and B particle collide with each other, but they are not able to produce a product because they might not have a sufficient amount of energy to chemically join with each other or combine with each other. So the minimum possible energy which the reactants required to form a product, what we call that? We call that as activation energy. Activation energy is the minimum possible energy which a reactants can have, or particles of the reactant can have, so that they can form a product. So according to collision theory, if we increase the effective collision, it's not only the collision, if we increase the effective collision, then the rate or the speed of the reaction will also increase. So as you can see here at the bottom, this is the energy profile diagram for exothermic reactions in which the reactants have more energy and the product is having less energy. And exothermic reactions release energy, give out energy. But even for exothermic reactions in which the particles tend to release energy, but they need, like the reactant particle A and B are the reactant particles, so they still need some energy to combine with each other. They don't have initially sufficient. So once they reach or get the sufficient energy, so the moment they get the sufficient energy, they have effective collision, a collision that will lead to a formation of a product. So they will collide with each other, and once they collide with each other effectively, as a result, it will form a product. But because the product which is formed here is having a low energy, so the remaining energy is lost to the surrounding. That's why this reaction is exothermic. So minimum possible energy which the reactant required to start up the reaction, to collide and form a product, what we call that energy as activation energy. So activation energy is a minimum possible energy for a reaction to start. Then we have a Maxwell-Boltzmann distribution graph for distribution of the energy between the particles. This is also known as a Maxwell-Boltzmann graph. Example, if we have the particles, so these are the reactant particles. So they all are not having the same amount of energy. Some particles will have high energy. Some particles will have low energy, but most of the particles will have average energy. You can understand this simply by taking example of the height of student in one class. Like if you are comparing the height of the student in one class, what you will find some of the students are tall, some of the students are short, but most of the students have an average height, like same height. So same thing happened for the particles, that when we have the reactant particles, so reactant particles, some of the particles have high energy, some of the particles have low energy, but most of the particle will have average energy. So when we sketch a graph for distribution of energy and the number of the particles, so number of the particles and the energy, so this will be the shape of the graph. So what it shows, what it represents, it shows some of the particles, because on the right hand side as we move, they will have high energy. Some of the particles will have low energy. And some of the particles will have high energy. But most of the particle will have average energy. Like most of the particles will have energy which is equal or same. Like if I say use the numbers, say this particle is having 20 joules of energy, maybe 21 joules of energy, another particle maybe 3 joules, 5 joules, 7 joules, but most of them have an average, like example 12 joules or 11 joules. So 12, 11, 12, 11. So when we create or work out the distribution for the distribution of energy for the particles, so we get this graph that which shows that some of the particles have high energy. So as you can see here, this is a Maxwell-Boltzmann distribution of energy among the particles. So as you can see, the Maxwell-Boltzmann energy distribution shows how the energy is spread out among the particles of a gas or a liquid at a particular temperature. So a few particles will have low energy because collision causes some particles to slow down. Like when the particles are colliding with each other, so these particles tend to slow down. That's why we call they have low energy. Then most probable energy, and this is not the same as a mean will be different, but most probable energy means like this is the energy which likely most of the particle have, but it does not mean it's an average energy, because average, when I take an average, like if I have number 20, 21, 22, 21, and then 3 and 7, so average will be more towards the higher side, because smaller amount of energy is less, most of them have greater energy. So when I take an average, so average will be more towards 20. That's why this energy is not called an average energy, we call that as a probable energy or most probable energy. Like most of the particles have this value, as on the y-axis is the number of the particles. So as you can see that most of the particles have this value or this amount of energy. And then after that there will be an average energy, like mean energy or average energy. Then area under the graph, what it represents, this whole area. If we want to calculate the total area of this graph, so what it represents, it represents the total number of the particles. How many particles of gas or liquid are there? That's known as the area under the graph. And on the right hand side, these are the most molecules have energy between the extreme, as it's not a symmetrical, like it is not a symmetrical distribution, like most have energy near the average value. And what is activation energy? Activation energy is a minimum possible energy at which the reaction start. So basically the particles after the activation energy, they will form a product, they will result in a formation of a product. But particles before that, because they have low energy, so they will remain as reactant, because activation energy is the minimum possible energy for reaction to start. So the particles which are having energy more than activation, they will form a product, turn into a product. But as a particle which have energy less than activation, they will just collide with each other, but their collisions won't be effective. The energy distribution go through the origin, because there is no molecule, like no molecule with no energy, like that is like when molecule is zero, the energy is also zero, so it should start from origin. And this should, the energy distribution should never meet x-axis, because there is no maximum value. Like I cannot say the maximum amount of energy for a particle is 100 joule. It can be 200, 300, 5000, any number, but it won't be any specific number. Is it clear, this graph? This is very important that you learn all the points of this graph. Any doubt till this point? Any question or a doubt? Now, what will be the effect on the shape of this graph? Like if we increase the temperature, if we change the temperature. So how can a reaction go to completion if the particles have energy greater than activation? So if we increase the temperature, what will increase in temperature increases the rate of the reactions. And as the reaction rate increases, or rate or speed of the reaction increases, the equilibrium, the number of the particles shifted more towards the higher side. So what we'll observe the peak will decrease, the height will decrease, and it is distributed more towards the right hand side. But the area will be same. Area of graph at lower temperature will be same as area at a higher temperature, because area is representing the number of particles. As the number of the particle does not change, that's why the area won't change. So what happened when we increase the temperature? Most of the particles have energy more than activation, or greater number of particles have energy more than activation. So this will result in a higher amount of product. So if I say there's a reaction, this is the activation energy. So for blue graph at 25 degrees centigrade, only this is a region where the particles are in contact with each other. So our particles are colliding, so small area is there, that's why it will form a product, but only these particles will react and form a product. But when we repeat the same experiment at around 1067 degree, so you can see the total area of the particles which are after the activation energy increases. That's why at higher temperature there will be greater rate of formation of a product as compared to that of lower temperature. Is it clear? So as the temperature increased, the distribution shifted more towards the higher side, or a molecule will have high energy. So both the probable energy and the mean energy shifted towards the higher side, which increase the rate or the speed of reaction. Is it clear, this part? Then if you want to measure, so only two factors are there which can affect this graph. Number one is the temperature, and number two is the catalyst.